In this video, we're going to look at writing the equation of rational functions from graphs. And it's going in the opposite direction as if we're performing the analysis of an equation, but our concepts remain the same. There's a step-by-step guide to how to do this, to try to make this process a little easier. What we try to do is we try to determine all of the factors of our numerator, which are the zeros of the graph and their corresponding multiplicities. We next try to determine all the factors of the denominator. So those are our vertical asymptotes and their corresponding multiplicities. And then we look for any holes, because holes will zero out both the top and the bottom. And after we get all of those factors put where they belong, we're then going to use either the end behavior or a clear point to identify a stretch or shrink factor from there. So let's look here at this first problem. Let me zoom on in here. So let's identify our vertical asymptotes and their multiplicities along with any kind of x-intercepts. Well, we have a vertical asymptote right here at -3. It's hard to see it because the graph didn't stretch down far enough, but there is one right there at -3. So at x equals -3, we have vertical asymptote. Notice how the left side and the right side both point in the same direction. Since both sides point in the same direction around the vertical asymptote, it has a multiplicity of 2. We also have a vertical asymptote, it looks like, here at x is equal to 4. Now, since the left side and the right side point different directions with their unbounded behavior, we're going to say it has a multiplicity of 1 there. Now, we know that vertical asymptotes zero out the denominator. So right now we know that there's an x minus 4 and a x plus 3 to the second power in the denominator. Now, let's go look at x-intercepts. There's an x-intercept at -2. So we got an x-intercept at x is equal to -2. It passes straight through there, so the multiplicity is a 1. There is an x-intercept at +1. Now it's a touch and a go. It doesn't change sides. It stays on the same side it was originally on, which means that there was a multiplicity of 2. And there are no other x-intercepts, so we can go ahead and put those factors where they belong. The x-intercepts are factors that make the numerator equal 0. So my numerator, I'll have x plus 2, and I'll have x minus 1 squared. Now, we need to find that vertical stretch factor, call it A. So I need to know what is that number of A that will account for the stretch and the shrink for the y values. Well, if we have a horizontal asymptote that is not the x-axis, what we can do is we can look at the end behavior to figure this part out. And especially since there's not a clear defined point for us to use. And so it appears to me that there is a horizontal asymptote around the x value of -3. Now, here's the part that some people get confused, is they were told that, hey, a graph cannot cross its vertical asymptote, but you just drew it an asymptote and the graph crossed it right there. So what? This is a end behavior asymptote here in green. Even though we call it a horizontal, it's an end behavior asymptote. Functions can cross their end behavior asymptotes in the middle parts of the graph, and even though it crosses it, we're only talking about x equals 10. The end behavior is describing the behavior of the function. We start getting a long ways away from it, so hundreds to thousands away. So since the end behavior, it looks like it heads towards the horizontal asymptote of y equals -3. What that means is that the ratio of the coefficients has to produce a y value of -3, which also tells me that my degrees between my numerator and denominator have to be the same. Well, I have degree 2 and a degree 1. That makes degree 3 in my numerator, and x squared and x make a degree 3 in my denominator, which means that for this problem, a is equal to -3. So I use the end behavior to get my stretch or shrink. So for this graph, our equation would be -3 times x plus 2 times x minus 1 squared over x minus 4 times x plus 3 squared. All right, let's look at another one and try to write its equation. So let's start with the vertical asymptotes. I look at for unbounded behavior. I see the graph get vertical here at x is equal to -3. Now, left and right sides go different directions, so the multiplicity is 1. The next place I see unbounded behavior is at x is equal to 2. So, and that also goes opposite directions. So at x equals 2, we have multiplicity of 1, and it looks like there's also a third vertical asymptote. Vertical asymptote at x is equal to 4. So I have my vertical asymptotes listed. Now, the vertical asymptotes, what they tell me is that in my equation here, I will have 3 factors. I'll have x plus 3, x minus 2, and x minus 4. Now we go look for x-intercepts. Let me grab a different color. So where does the graph cross the x-axis? And I only see one place it crosses the x-axis, and that looks like it crosses at -1. And so we want to determine what the multiplicity is of that function right there at -1. And we can say that since the function touches and doesn't change sides there, we can say that that multiplicity is 2. So we have an x-intercept at x equals -1, multiplicity of 2, which means that we take that factor, x plus 1, and we square it. There's no other x-intercept. And so we're done with that part. Now we look, and there's a hole identified for us. We have a hole at x is equal to 3. Remember that holes zero out the numerator and the denominator at the same time. So I got to put that factor, x minus 3, in the numerator and in the denominator of the fraction. So we have this rational function constructed. All we have left to do is to determine this vertical stretch or shrink factor. Well, unlike the previous problem, we have a end behavior asymptote of y equals 0, which means that the degree of the denominator has to be bigger than the numerator. So you count your x's. I have 3 x's in my numerator. My denominator have 1, 2, 3, 4 x's down there multiplying together. So I have x to the third divided by x to the fourth. Bottom heavy makes y equals 0. So what we have to do is we're going to have to determine a based on the fact that I have a hole that has a y value of -2 and 2/3. So the y value of that hole is -2 and 2/3, which is -8/3. So the way we would solve for a is we're not just going to put -8/3 in for a. Was through the process of finding the y value of the hole, we would cancel out the factors, which would make us have a times x plus 1 squared over x plus 3 times x minus 2 times x minus 4 is equal to y. And now that we've removed the hole, that means when we put in 3 for all the x's, we should equal the y value of -8/3. So -8/3 is going to equal a times, and I'm putting in the x value of the hole, which is 3, everywhere there's an x. So 3 plus 1 squared over 3 plus 3 times 3 minus 2 times 3 minus 4. I'm solving for a. So I have a times 16 divided by 6 times 1 times negative 1 is equal to negative 8 over 3, which this problem becomes basically, and if I reduce the right-hand side, I have, reduce everything by 2, I got negative a times 8 over 3 is equal to negative 8 over 3, which means a is equal to 1. Well, how about that? So there actually was no stretch or shrink, and a was 1, so our equation, basically, we go back up to the very beginning, and we just let a be 1, and so our final answer is going to be x plus 1 squared times x minus 3. I leave the factor that makes the whole in there. I don't want to write my final answer as the simplified answer in this case, because then you would not be accounting for the whole. So here's my equation of that graph that was given.